All right, hello everyone. So let's talk about our next lab, which is going to be on conservation of momentum or conservation of linear momentum. So let's first talk about what is momentum, and then we'll talk about how it's conserved. So momentum is a quantity in physics that represents product of mass of the object and its velocity. So for example, let's say there's a box that has a mass of 2 kilograms moving with the velocity of, let's say, 5 meters per second. Momentum is a product, let's represent lowercase p for the momentum. It's a product of mass of the object times its velocity. So momentum is just like velocity, is actually a vector quantity. So momentum, is a vector. What do we mean by a vector? Remember, vector is directional quantity. That means, for example, if the velocity right now is to the right, I take the right to be my positive x direction. So that means I have to say that this is plus 5 meters per second for the velocity. That means for the momentum, I will have the mass, which is 2 kilograms times the velocity, which is plus 5 meters per second. So then this will be in terms of 2 times 5, which is 10 units of kilograms times meter per second. So this will be 10 meters per second times kilogram, or kilograms times meter per second. And since this is plus, this is also plus, indicating that momentum is also in a positive x direction. So if we want, we can put horizontal component or the subscript right out to the momentum. That means momentum itself, again, so momentum is a product of mass times velocity. And this is an information about, in a way, how the object is moving. Let's say faster it is moving, you can see that from the equation, the greater the momentum of the object. Also, how big the object is. It can give you sort of like, let's say, double information about the velocity, how fast, and also how big the object is. This is generally useful when we're dealing with, for example, collisions. When you have collisions, then the best quantity to use is the momentum, because the momentum obviously will give you collision information for example, fast moving but a very light object, or maybe fast moving and a big object. Imagine, let's say you're going to be let's say there's a wall over here, and then two objects represent them. Let's say represent them as a particle. So two objects moving at 2 meters per second at the speed of 2 meters per second toward the wall, and they're going to collide. Okay, so the question is that which one will give us more damage to the wall? Well, just knowing how fast those objects are moving is not enough information. We have a 2 meters per second, which is roughly 5 miles an hour. Okay, so it's not a big, let's say it's not a big speed, but still, if I tell you that, for example, one object is a mosquito moving at 2 meters per second and colliding with the wall, you can imagine that's almost nothing, no damage to the wall. But second one could be an elephant moving at 2 meters per second and hitting the wall. Now that can do a lot of damage. That means including the mass along with the velocity gives us more information, especially like, let's say, dealing with things like collisions. So that means momentum itself is a quantity that is a vector, as I mentioned, so directional. That means if the object moving to the right, momentum is positive. If object moving to the left, momentum is negative. We're going to be constraining ourselves with just the horizontal motion. So that means when I say positive, negative, it's just going to be to the right or to the left. So for example, then, if we have that box, right? So let's say moving to the right with the velocity of, was at 5 meters per second, and it's positive, and the mass here is 2 kilograms, then again, what we said here, momentum is mass times velocity, which is 2 kilograms times 5 meters per second. This gives us 10 plus 10 kilograms meter per second. Okay, and generally in along with this quantity, the quantity momentum, we also talk about, let's say, what will happen to the object. So that means, let's say when it's moving and maybe colliding, or just in terms of its motion along the horizontal axis. So let's say when we have this information, 10 kilogram meter per second, that just means that in this particular context, right, you have a 2 kilogram object moving to the right. Okay, so in a way, this is an instantaneous quantity. That means it just tells you at this instant of time, and technically and also position, right? So let's say this object is moving at this speed and it has this much mass, so momentum is this much, which is 10 kilogram meter per second. At some later time, other things can happen, and then we can figure out what technically happens by looking at the momentum at some later time. So let's say this is at position x1. So then let's say then I can say that this is velocity 1, and then some position x2, I can figure out what happens if I look just this quantum momentum, which means this momentum right now that we calculate will be momentum specifically at point 1. Okay, that means this is object at position 1 moving at 5 meters per second, and it has a momentum of 10 kilogram meter per second. Now, if I tell you that momentum at point 2, for example, is 5 kilogram meter per second plus, well, that already tells you that when the object gets to position 2, its momentum decreases. All right, so remember, momentum decreases is still same quantity in terms of mass times velocity, but this is mass times velocity at point 2. Now, we already know that object has a mass of 2 kilograms. That means what I have here is the new momentum at point 2 is 5 kilogram meter per second. And it already had 2 kilogram, assuming that it doesn't change its mass. That means the only reason its momentum decreased because its speed decreased. So in this particular case, the speed is if speed is 2.5 meter per second, then it will match to 5 kilogram meter per second. That means we had the speed going down from 5 meter per second to 2.5 meter per second. An object, has a lower momentum because its speed is less than before. That means what happens here between x1 and x2, the object's basically slowing down. So this is known as a change in momentum. So it's change in momentum, delta P, which means we're going to see that how momentum changes between points 1 and 2. So P2 minus P1. And this quantity is another way of looking at the motion of the object. Obviously, if at point 1, I have a momentum of plus 10 kilogram meters per second, and at point 2, I have a 5 kilogram meter per second, well, you can see that momentum has decreased. Momentum has decreased. And the momentum can decrease either by decrease in mass or decrease in speed. Assuming that mass is, let's say, not going to change because you have just one object that's going to be moving back and forth. Decrease in momentum means just is moving slower. That means you can look at this particular change in motion from the momentum point of view. Previously, we talked about if there is a decrease in velocity of the object, that was due to an acceleration. Acceleration will change your velocity as a function of time. Well, then we talked about forces, and we said, okay, so this acceleration comes from the force because there is, this acceleration due to some kind of net force, acting on the object that has mass m. But this way of looking at the motion is a little bit different from the acceleration and Newtonian dynamics that basically still represents change in motion due to an acceleration. Here we're going to talk about how Newton technically wrote down his Newton's second law. Right now, this is the version that we use as a Newton's second law. Isaac Newton wrote this Newton's second law from the perspective of momentum. He said that you decrease your velocity because there is a change in momentum, rather than, let's say, there's acceleration. Now, question here is what changes the momentum of the object, delta P? Now, if I'm changing the momentum of the object, which in case you can see, right? So we went from 10 kilogram meter per second to 5 kilogram meter per second. So it's a decrease of momentum. And decreasing momentum as a function of time, because this was my T1, this is T2, right? It takes time for the momentum to change. Now, Newton says that the factor, or the quantity technically, or the reason the momentum changes because there's some kind of force acting on the object, some kind of non-zero net force. That means there has to be some kind of force acting on the object, so it changes its momentum from 10 to 5. That means this is kind of similar to this, let's say, Newton's second law equation, where there's a change in momentum is due to force. We're just not using the acceleration anymore. We are using the momentum as a quantity rather than acceleration as a quantity. That means change in momentum can be written, if I cross multiply both sides by delta t, is because there's a force acting on the object during this short period of time, delta t. So that means this is an equation that's known as a equation for the object momentum change. That means you change your momentum, or the object changes momentum, because of a force acting on it, but force takes time. So almost, if you're slowing down from, 5 meters per second to 2.5 meters per second, it doesn't happen instantaneously. It takes a little bit of time. And what changes your speed or changes your velocity or momentum, they're all the same, right? The reason is the force. Now, this is also sort of like at the beginning of what we're going to use as a conservation of momentum. The idea here is that momentum quantity as mass times velocity, but much more important, let's say, information we get from looking at the change in momentum. Change in momentum, which is written as delta P. This means that object's momentum 2 you can think of as like after, minus object's momentum 1, which can be like, let's say, before. So after or before, right, compared to before and after, is due to some kind of force that was acting in some short time interval. Now, this force sometimes also known as external force. External force. That means there has to be some external force. Now, if you really think about it, let's say if you have a box moving from point 1 to point 2 and it's slowing down, most likely that force is maybe a friction, right? So that means going from point 1 to point 2, there was a friction acting in the opposite direction. So during this displacement, right, during this displacement going from point 1 to point 2, the friction was slowing it down. That's why when it got to point 2, it was moving slower. In this case, this force is that external force, this friction. So this friction is external force responsible for changing the speed or the velocity of the object, which directly goes into changing the momentum. Okay. That means to change the object's momentum, you need external force. All right, so hopefully we're clear on that. Now, to understand then collisions, we can look at system of particles, not just one object. Obviously, for colliding, in order for us to have a collision, there has to be, two objects, right? Two objects colliding or three objects colliding. So let's talk about two objects colliding. So let's say we have object 1 and object 2. Okay, so they're going to collide. Generally, what we can think of here is they are on a smooth frictionless surface. Okay, let's ignore friction for now. So no friction, because we know, right, the friction is an external force and it can, decrease the momentum of the object. So let's say there's no friction. Okay, because what we're doing here, we're looking at a system. This is my system where I take both of those, objects in, part of my system. And let's say right now, one of them moving to the right, so this is V1, it has a mass of M1. The second one, for example, can be moving to the left. So this is V2, it has a mass of M2. And obviously, if they're moving toward each other, they're going to collide at some point. Now, what I can say here, this is representing before collision. So this scenario, right, represents before collision. They're moving and they're going to collide at some point. Now, what we have here is I can represent momentum of the first one as M1 times V1. Momentum of the second one is M2 times V2, because each one has mass and velocity and the product is momentum. But I can also represent momentum of the system before. Let me put I for the initial. This PI without subscript 1 or 2 represents the momentum of the system before collision. So this is then equals to momentum of object 1 before the collision. I is a subscript initial, right, before the collision, plus momentum of the object 2 before collision. That means in order to calculate the total momentum of the system, I need to take each momentum of object 1 and object 2 and add them together to get the total momentum of the system. Okay. Now, what I have here is then, let's say this will be mass 1, velocity 1, because initial momentum is mass 1 and velocity 1, but I'm going to also put subscript I indicating the initial velocity. Then plus the momentum 2 initial will be then M2 V2 initial. Mass 2 times velocity 2 before the collision, so I put initial subscript. That means this will be the expression for the initial momentum of the system. Okay. Then obviously they're going to collide. So this is thing like this. So this was before, and this is going to be then during. This is going to be a picture of during the collision. So they're going to collide. Okay. And when they collide, they're going to hit each other with some force. And that force is, let's say this will be the force that object 2 exerts on object 1. This will be the force that object 1 exerts on object 2. Remember, this is object 1 and 2. That means, when two objects collide, they hit each other with the force. But that force is, according to Newton's third law, is called the action-reaction force. Which means for every action, there's equal but opposite reaction. That means, for example, if I'm doing the net force, where I'm adding those two forces, F12 is to the right, it's positive, then minus F21, so it's to the left, so it's negative. What I will get here, I will get 0. Because for every action-reaction forces, when you add them together, you're going to get 0. Because if F12 represents force that, object 1 exerts on object 2, F21 represents the force that object 2 exerts on object 1. Those are forces that they exert on each other during the collision. Those are also sometimes known as the internal forces. And always internal forces sum up to 0. So that's why this is my system, and the system has two objects, and during the collision, they strike each other with force. But if I add those two forces together as the net force of my system, I will get 0. I will get 0. Now, let's say then what happens after the collision. Well, after the collision, what I will have here is this. Well, let's say box 1 will start moving to the left, V1 final. Box 2 will start moving to the right, V2 final, because imagine, right? They're moving, they collide, and then bounce back. That means momentum of 1 after the collision, so then I can say final, equals M1 V1 final. Momentum of 2 after the collision will be then M2 V2 final. But then I will need to add them together, and when I do, to get the momentum of the system final, it will be momentum of the initial after the collision plus momentum of the final after the collision. So M1 V1 final plus M2 V2 final. That means each momentum for each object, right, is added together to give me the system momentum. All right. So that's what we get. So that's the expression, momentum. This is momentum before, again, of the system, and this momentum after the collision. And here's then what we have. We learned that there will be change in momentum. That means, for example, right? So there will be, let's say, delta P, change in momentum, P final minus P initial. Momentum of the system after the collision minus momentum of the system before the collision. And we learned that this will be due to some kind of force, net force, acting during the short period of time. And delta T is always represent the time of the collision. How long did it take for them to, be in physical contact? But here's what we get. We just talked about how those forces are internal forces, and they cancel each other. That means my net force is 0. That means this right side of the equation is 0. So momentum of the system after the collision minus momentum of the system before the collision equals 0. So this represents conservation of momentum because there is no difference between them, right? Only if two quantities are the same, their difference will be 0. So this means that momentum of the collision, momentum of the system after the collision is same as momentum of the system before the collision. This is, representation of the conservation of momentum. So doesn't necessarily mean that each individually they conserve the momentum. The system of, two particles, right? Two objects together conserve momentum. That means I can write this. So you can see, right? Here's, of initial momentum. Here's final momentum. So final momentum was M1 V1 final plus M2 V2 final, which means this is the momentum of the system after the collision. This is going to be exactly same as the momentum of the system before collision, which was written as M1 V1 initial plus M2 V2 initial. That means this equation is sort of like a general equation for the conservation of linear momentum. Okay, so now one of the things we're going to do here is we're going to look at type of collisions. And there are two types of collision. One is elastic. The other one is inelastic. And this equation can be used for both of those type of elastic and inelastic collisions. Okay. Now, in this particular lab, we will be working with inelastic collision and a special case of an inelastic collision. So that means momentum is conserved for both collisions, elastic and inelastic. Momentum is conserved for both of those collisions. But in the inelastic collision, there is a special case where objects stick together after the collision. That means, for example, if you have object 1 and 2, this is before collision, and they could be moving toward each other or moving away from each other. Well, at least one of them moving away, let's say, or one of them can be at rest. And the easiest case will be this: object 1 moving with some initial velocity to the right. Object 2 is initially at rest. Its velocity is 0. Imagine, right? Something is sitting there, and then second box is moving toward the second one. Sorry, the first box is moving toward the second one. So obviously they're going to collide. But what happens here after the collision, that means we can right now ignore what happens during the collision, because during the collision, you only get internal action-reaction forces and they cancel each other. So we don't really care about what happens, during the collision. See, our equation here shows that all we care about is before and after. So this is before and this is after. And it's even those, right? Momentum of the system before and after is exactly the same. So we can just ignore what happens during the collision. That means in this particular example, so we call it perfectly inelastic, or sometimes completely inelastic. So perfectly or completely inelastic, object then will stick together, stick to one another, and then they will be moving with some final velocity. Okay, that means they're going to move with some kind of final velocity. What happens here is this: momentum of the system before collision. So let's say P1 or P initial. This will be M1 V1 initial plus M2 V2 initial. This is the general equation, right? Momentum of the system before collision. So that's the momentum of the first one in terms of its mass and velocity. There's momentum of the second one in terms of mass and velocity product. But we know that second object is at rest. That means what I have here is then this is going to be M1 times V1 initial plus 0. Because momentum of the object 2 initially is 0 since its velocity is 0. So the whole thing is 0. That means object 2 has no momentum before collision. Because if you don't have velocity, you don't have momentum. So one thing we can do then, we can say that initial momentum of the system just M1 times V1 initial. Okay, that means how fast it's moving. So for example, let's say this guy is moving at 5 meters per second and has a 2 kilogram mass like we did before. That means this will be 2 kilograms times 5 meter per second. So then this is going to be 10 kilogram meter per second. Now, one thing I have here is I can assume that this object 1 will not change its speed until it reaches and collides with object 2. And the reason, because remember we talked about it's a frictionless surface. There is no friction. It's not going to slow down. So if I say that object 1 is moving before collision 5 meters per second, it means all the way until it collides with object 2. Okay. Now, momentum of the system after is then those two colliding, sticking to one another and moving with some final velocity, because they become just one object, one blob. And in that case, I can say that their mass, the total mass of the system, is just m1 plus m2. So let's say if object 2 has a mass of 3 kilograms, then I can say that m1 plus m2 is then 5 kilograms, which is the total mass. That means this is just basically time, total mass, right? Times then final velocity, because momentum is still mass times velocity. But now the total mass is combination of mass 1 and mass 2 together, because they entangle or they stick together, right? So then what I can say, this is basically equals to m1 plus m2 is 5 kilogram, then times v final. Okay, then what I have here is, we don't know, for example, what the v final is. We don't know what's the velocity of this object after the collision. But I know one thing, that because there is no friction, it's a conservation of momentum. That means momentum of the system before and after are exactly the same. Which means that I can say that momentum of the system before is 10 kilograms meters per second, and momentum of the system after is 5 kilograms times v final. That means this is the total momentum of the system before collision. This is the total momentum of the system after the collision, but it's a product of mass times velocity. I just have the mass, but not the velocity. Then all we have to do is just solve for velocity. That means divide both sides by 5 kilograms. And then I can say final velocity is equals to 10 kilogram meter per second over 5 kilogram. This gives me 2, we can say kilogram cancel out, so 2 meters per second. That means those two together after the collision gonna stick to one another and move with 2 meters per second speed. Okay, that means this is basically what we're going to be able to see in the experiment. 2 objects colliding where one of them is at rest initially. Then we can say that momentum is conserved because initial momentum and final momentum are exactly the same. So then what we're going to do here is we're going to use that information to calculate the final velocity of the system. All right, so to verify, you can see, right? See, initial momentum was mass 1 times velocity 1 initial plus mass 2 velocity 2 initial. Well, this was 2 kilograms times 5 meters per second plus 3 kilograms times 0. So then what we end up here is 10 kilogram meter per second plus 0. So 10 kilograms meter per second. This was the momentum of the system before, which is 10 kilogram meter per second. Exactly same thing I should get them for final momentum. So final momentum is equals to, but remember, they stick together and move as one. So that means m1 plus m2 times v final. So then this is 2 kilograms plus 3 kilograms, then times v final, which we just calculated as 2 meters per second. Let's verify if then the right and left sides are correct. Then you can see, right, this will be then 5 kilogram for the mass, then times 2 meters per second for the velocity after the collision. And what we get here is 10 kilogram meter per second. Same before and after. So that's why we can say the momentum is conserved, which just means that it's same quantity before and after. All right, so let's then go and look at the experiment itself. So in this experiment, we're going to be looking at, again, conservation of momentum. And we will be looking at the inelastic collision, where we are looking at the video, you can see, right, of a complete collision, where you have the blood wart and a low cart friction friction cart, which means that we can ignore the friction. It's small enough that we can ignore it. All right, so the experiment itself is basically going to be a blow dart going to be shot toward the stationary, let's say, cart. So you can see, right? So the first trial is a demo. So we're going to be using this as a preliminary, learning about the system and everything. So trial one is a demo. So using that, we should be able to see what's going on. So let's watch the video. There you go. So this is the whole picture of the experiment. So if you kind of go back, so see, so like let's say here's what I have. You can say that this is before the collision. M1, V1 initial. This guy here is our M2, V2 initial is going to be done 0 because it's not moving. So our goal will be to understand sort of like, let's say, what's going on, right? Because you can see that object 1 is moving at constant speed until it collides. So this is before collision. And then what I will have here is, and this is the collision, the instant of the collision, and then they're going to stick to one another, right? See, then after that, the system moves as one. Let's see. Sorry, I have technical difficulties here for 1 second.